Welcome to part 2 of Choppers. This is unit 3 of power electronics. In this video, step-up chopper is discussed in detail. The step-up chopper is also known as the boost converter. So in case of step-up chopper, we start with some assumptions before analyzing the circuit. That is the steady state condition they exist in the circuit. The inductor current is continuous, which means it is always positive. The capacitor is very large, so output voltage is almost constant. The components are ideal, and we analyze it further by first studying and deriving the inductor voltage and current when the switch is closed and then when the switch is opened. Let us see the circuit configuration of step-up chopper. The step-up chopper is also known as boost converter. The circuit diagram for boost converter is as shown in the figure. Now here the inductor comes in series with the supply voltage. Chopper is connected in parallel. Diode is connected in series in between the inductor and the load capacitor. So when the chopper is on, at that time, the inductor, it stores energy. When the chopper is off, the inductor energy is provided to the load along with the supply voltage. The purpose of the diode in the circuit is to ensure that current doesn't flow from capacitor back to the source. The detailed working of the circuit is presented here. When the chopper is on, the supply voltage comes in series with the inductor. The diode is reverse biased, so the supply voltage is disconnected with the load. So the voltage across inductor during this time is equal to Vs. When chopper is off, the supply voltage along with the energy stored in the inductor, it is provided to the load. So the voltage drop across inductor is Vs minus V naught. If we observe the inductor voltage, it is positive equal to Vs when the chopper is on and Vs minus V naught when the chopper is off. The current through the inductor, it rises when the chopper is on from I minimum to I maximum, and it falls from I maximum to I minimum when the chopper is off. The diode current is equal to the inductor current when the chopper is off. But when the chopper is on, the diode is reverse biased, hence the diode current is 0. The capacitor current, if we observe, when the chopper is on, during that time capacitor is providing the current to the load. So current from the capacitor will be equal to V naught upon R. When the chopper is off, during that time the capacitor is charging. So the current waveform of the capacitor, it follows the current provided by the inductor. Also, here duty cycle is represented by capital D. It is equals to T on upon T. So on time can be given by dt, and off time is T minus dt, which is equals to 1 minus d into T. So when the chopper is on, that means the switch is closed. This is the circuit. So inductor current is flowing due to the supply voltage, and the drop across inductor is Vs. So we can write it as the inductor voltage is equals to Vs, which is L dIL upon dt. So the delta IL upon delta T becomes equals to Vs upon L, and delta T is actually the on time, which is written in terms of duty cycle as D into T. So I can ensure that delta IL closed here is equals to supply voltage into duty cycle into switching time period divided by inductor. When the switch is open, this is the circuit. Now the voltage drop across inductor is Vs minus V naught, which can be written as LdIL upon dt. Now here delta t is equals to 1 minus d into t. So I can write down delta IL close open equal to Vs minus V naught into 1 minus d into the switching time divided by L. The value of delta IL open and delta IL closed can help us in analyzing the circuit in steady state. So in steady state, the sum of inductor current will be equal to 0. So we have already calculated delta IL closed and delta IL open. We'll substitute the values and we can solve the expression for the value of V naught, which comes out to be Vs upon 1 minus d. So we know that duty cycle here is T on upon T, which is less than equal to 1. So output voltage will be always greater than the supply voltage in case of boost converter. So boost converter provides the output voltage which is greater than the supply voltage. Also, the average current in inductor is not equal to the load current as in the previous case, because here when the switch is on, the inductor is disconnected with the load. So here we take the concept of average power here. So we will see that in the steady state, the average power supplied by the source must be the average power absorbed by the resistor. So let us see what is the output power here. Since the output is a resistive load, so output power can be given as V naught square upon R. And input power is Vs into Is. You can note down that whether the chopper is on or the chopper is off, inductor always comes in series with the source voltage in this case. So we can replace the source current with the inductor current IL. Equating both the equations, we can find out the value of IL as Vs square 1 minus d whole square into R. So the average inductor current can be determined using the equation here. So further using IL, we can find out the Imax and Imin value, and delta IL we have already calculated. So using the expression of IL, Imax and Imin, we can further determine the value of L. So in Imax, I can put delta IL, which is equal to Vs dt upon L. I am using here IL closed expression. So I minimum can also be determined using the expression here, and using the boundary condition of continuous and discontinuous current mode conduction, if we substitute Imin equal to 0, I can find out the value of L minimum, which comes out to be d into 1 minus d square into R upon 2f. Notice here that switching frequency is again in the denominator. Let us find out the value of C in the circuit. So to find out the value of C, we use the waveform of IC. In the waveform of IC, we can see that there is a different wave shape in a positive half and a negative half. And the waveform in a negative half is the area of the waveform in the negative half is simple a rectangular area. So we will use this half cycle to determine the value of delta Q. And since here IC is minus V naught upon R, so we will use mod of delta Q instead of delta Q. So finding mod of delta Q, which is V naught upon R into dt, that is the area, which can also be written as C into delta V naught, we can find out delta V naught is equals to V naught dt upon R into C, where 1 upon T is written as the switching frequency, and delta V upon V, which is the percentage ripple factor, is equals to D upon RCF. Also, C is equals to D upon R, percentage of ripple factor, into the switching frequency. So kindly note that switching frequency is in the denominator, and in case of inductor also it was in the denominator. So here also I will like to point out that if the switching frequency is high, the lower value of capacitor and inductors are required. So let us see one example based on this, a numerical example, where we have to design a boost converter that can produce output 30 volt from an input supply voltage of 12 volt, and the load resistor is 50 ohm. So first of all, what we can do is, if we know the output and input voltage, we can determine the duty cycle using the expression of boost converter, which is V naught is equals to Vs 1 upon D. So D is derived as 0.6 in this case. Now let us assume the switching frequency to be 25 kilohertz. In some cases it is given in the numerical, but if it is not given, you can just assume a frequency higher than the audio range and calculate the minimum value of inductance. When the duty cycle is known, the input output voltages are known, and the switching frequency is known. So L minimum is derived. The value of load resistor is also given as 96 microhenry. Also, inductor current can be calculated, because we want to find out that what is the minimum IL minimum in the circuit. So to keep the margin and to ensure that current is always positive, we select a higher value of inductor, because L minimum is a critical value. So we have to select a value which is higher than this, and it should be one of the standard value of inductor which is there in the market. So let us say it is L is equals to 120 microhenry in this case, and if we select L is equals to 120 microhenry, then what is I minimum? It can be calculated first by finding out delta IL upon 2, which is 1.2, using all the values, and particularly L here is taken as 120 microhenry. So I minimum is 1.5 minus 1.2, which is 0.3, and it is above the zero level. Capacitance is to be calculated by limiting the output ripple voltage to 1%. So delta V naught upon VO is equals to 1%, so 0.01. D we know, R is given, frequency we have taken as 25 kilohertz. So C comes out to be 48 microfarad. So C also you can select a higher value which is more than 48 microfarad. So L minimum calculated in this equation, calculated from the equation, and C minimum are the critical values. So usually we select the higher values of L and C in the circuit. Thank you for listening.